Okay, thank you very much. My name is Onderka, and I'm a PhD student at the Czech Technical University in Prague. And together with my supervisor, Stefan Ratschan, from the Czech Academy of Sciences, we have written the paper Fast Three-Valued Abstract Bit Vector Arithmetic. I will start by saying what we mean by the three-valued abstraction. Basically, we mean that we represent all bits in the state space of basically the model that we are simulating by abstract bits that can have three values, 0, 1, or x. And x means that the bit can have either the value of 0 or 1. And I will start with an example to kind of get an intuitive understanding of what we are trying to do. We are trying to generate a single three-valued bit vector operation output for arithmetic operations. And we want to do it quickly and with the best results. So first, the example. We have two abstract bit vectors, head A and head B. And we want to compute basically their addition. And we want to get the best three-valued abstract result at R best. So if you look at head A, that's x0, head B is 1, 1. So since we have x in head A, we have two possibilities of A being either 0, 0 or 1, 0. And B is 1, 1 in both cases. So we add those concrete bit vectors together, and we get possible results 0, 1, 1 and 1, 0, 1. And the three-valued results, because we want to have a single result, is xx1. So what we are trying to do is compute the best result in polynomial time. Because as we have seen with this, if head A or head B consisted of more x values, then this kind of naive algorithm would have exponential time based on the number of unknown bits. And I will go back to our motivation, why we are doing this exactly, and then go to a little bit of formalization before talking about our results. So our motivation was to formally verify conventional digital processor machine code, where we have movement instructions, we have bitwise logic, we have wraparound arithmetic and branching. Some other instructions are there, but they are not that important. We want to generate the state space of such machine code execution explicitly, but trying to avoid exponential explosion. So we use the three-valued abstraction, and we want a single result of every abstract operation. And in this talk, we will be focusing on forward direction without any backtracking at all. Now, previous results have already shown that movement and bitwise logic can be performed in linear time. This is doable by standard clean three-valued logic. And wraparound arithmetic wasn't actually considered much. The most interesting result was that basically the operational results can be pre-computed for 8-bit inputs and stored using binary decision diagrams. But this is obviously infeasible for larger inputs, and it is not very feasible for the 8-bit inputs as well. So we want to do better. Now, a little bit of formalization. We will formalize the abstract bit values as the sets of their possibilities. So 0 will be the set of 0, and x will be the set of 0 and 1. And abstract bit vectors will be just tuples of abstract bits, and we are using the IEEE standard logic notation, where basically the bit vectors, the abstract bit vectors, are denoted by double quotes and abstract bits by single quotes. And we will also define a concretization function for abstract bit vectors, which basically just gives us all the concrete bit vectors that are basically contained in the abstract bit vector. So for example, if we have x10, then this gives us these 4 concretizations we can see. Now that we have done all this, we can define the forward operation problem. I will simplify it here. Basically, for a given binary operator R, which can be the addition, multiplication, or something other, we have 2 concrete n-bit inputs and concrete m-bit output. And we have 2 abstract inputs, head A and head B. And we want to find an abstract result, head R, such that basically in the equation 3 it says, for every possible abstract input concrete input combination, if we compute the result of the binary operator, then it must be contained in the concretization of head R. And this brings us back to our example, where if we want to minimize the concretization of head R, we will call the head R the best abstract transformer due to our formalization. And I have already said that the naive computation is in exponential time. Even if we basically make it a bit better by only considering the x values, then it's just worst case in exponential time. And this was the example just with the actual possibilities. So back to our question, can the best result be obtained in polynomial time? Well, we have done our research, and our results are that for addition and multiplication, yes. And we assume that a traditional processor is performing verification, and every input and output bit vector fits in the machine word of it. So if this doesn't hold, it might have some linear time slow down or something like that, but it's polynomial time as well. So if this holds, the best abstract transformer of addition is computable in linear time, and of multiplication in worst case quadratic time. And we actually have found the algorithms that can do this and have implemented them. I will talk about the results more at the end of the talk, but basically the fast algorithms are quite fast even for 32-bit inputs, and the naive computation is almost infeasible for 8-bit inputs and more. And the memory is non-issue for all of the algorithms, as only a small fixed amount of temporary variables is needed. Now, how will we do this? How will we obtain the fast algorithms? Well, we had an idea to do a pseudo-Boolean reinterpretation. Basically put, a pseudo-Boolean function is a function which has Boolean inputs and an integer or real result. So we will reinterpret the concrete operation function R as a pseudo-Boolean function H, which basically gives the output as the unsigned number that basically corresponds to the output of R. Now, we will use a tuple of new functions hk for every output bit k, and each of them will be congruent with h modulo 2 to the power of k plus 1. And I will return to why do we do this. Now, after we do some wiggling, we can arrive at the equation 4, which gives us the equivalent best abstract transformer formula using hk. And it's not really needed to think about it too much, but I will just point out that each bit k can be considered completely separately, which I will do for the rest of this talk. And we can visualize the inequalities for a single bit k by basically putting the hk on a number line. And we can see that basically for the inequalities, we have like these yellow areas and blue areas. And in the yellow areas, the first inequality holds, and in the blue areas, the second inequality holds. And if we have some kind of concrete input possibility that basically has output of hk in the yellow area, then 0 is in the best abstract output bit k, and if we have some kind of a possibility that is in the blue area, then 1 is in the best abstract bit k. So what we can do with this? We can now formulate a modular extreme finding technique. And I will first define a step size as an absolute change of pseudo-Boolean function value when just one bit is flipped. And what we can do with this? If we restrict hk to the step size at most 2 to the power of k, and then we consider the previous modular inequalities here, we can basically look at it like this. If we look at the extremes of hk, the minimum and the maximum, 3 things can happen. Either the minimum and the maximum are both in just one of the areas, the same square, and then it is obvious that only one of the inequalities holds ever. Or we can have the minimum and maximum in a differently colored area, and then trivially both of the inequalities hold somewhere. Now, if we have both the minimum and maximum in the same colored area, but not the same exact area, if we have the restriction of the step size to at most 2 to the power of k, what must necessarily happen is when we are going from the value that gives us the minimum to the value that gives us the maximum, we must step at the blue area somewhere in between. So what we can conclude from this is that basically if we reach the minimum and maximum in the exact same area, in the exact same square, then only one of the inequalities holds and gives us output 0 or 1, and otherwise both of them hold. So we can conclude is that we only need to find the extremes of hk to get the best result. And how will this help us? Well, for addition, the pseudo-Boolean operation function is defined like this. Basically, we take all the bits, we scale them based on the position of the bit, and we add both the bit vector a and b together. Now, if we want to make sure that each hk is congruent with h modulo 2 to the power of k plus 1, but every step is at most 2 to the power of k, we can just remove the summands with coefficient divisible by 2 to the power of k plus 1. And this will give us the hk functions for addition, just like that. And we can see that finding minimum and maximum of this in linear time is trivial if we are given some head A and head B, because there is only one variable in each summand, so we won't know how to minimize and maximize trivially. So this directly leads us to the fast algorithm. That is quite nice. And we can similarly do subtraction and summation with multiple independent operands. So that is very nice. And we can see the example of the fast abstract addition here, what we now need to do for the lowest significant output bit. Well, we now have the h0 where we have tossed out the summands that are divisible by 2. So we just have 0 plus 1. The minimum and the maximum is 1. That lands in the same blue square in its corner. So we can conclude that the result is 1. And if we have the second lowest significant bit, then basically we now have h1 x0 plus 1, 1. Now, if we minimize, that is 0, 1, and the maximum is 1, 1. And as we can see here now, the minimum and the maximum is not lying in the same area, so we basically just need to do some some tossing out of the least significant bit of the minimum and maximum here, because the squares now are of length 2, not 1. But then we just get that the best result is x. So that was very nice, but the next part, the multiplication, will not be nice at all. First, we could try a non-best approach, where we would first have an idea that we could perform multiplication via summation, basically by rewriting multiplication to summation by long multiplication. But we can quickly see that this does not result in a best abstract transformer. And here is the shortest counterexample. Basically, what happens is B1 is carried through ripple carry to the next bit, and then we get to B1. But the summation no longer knows that both B1 are dependent on each other. So it produces x1, where the best result should be x0, x1. So if you look at it for 8 input bits, we can compute that about 16% of results are unnecessarily over-approximated. So what can we do with this? Well, we can go back to our fast extreme finding technique and doing things right. So the pseudo-Boolean operation function for multiplication is as in equation 7. And we could try to just remove summands that are divisible by 2 to the power of k plus 1. And this is congruent, obviously, with h, modulo 2 to the power of k plus 1, but does not work for extreme finding, does not result in the best abstract transformer, because the step size is just too big. But we can do another thing. We can also flip the sign of 2 to the power of k coefficients. So we arrive at equation 9, where we basically have how we will define the functions hk for multiplication. And now the step size is at most 2 to the power of k. Now, if we have this kind of equation, we want to find extremes. So how we will do it now? Well, that's quite problematic, because how we should go with extremes now depends on the values of variables that form summands 2 to the power of k, ai, bk minus I. And since those two bits interact with each other, it is not readily apparent what we should do. So what we had to do was to prove that if at least 2 of these pairs of these summands that have both abstract bits x exist, then this immediately implies that the output of the kth bit is x. And otherwise, we can now continue quite normally. We can minimize or maximize the single unknown k-column pairs and treat the possibly remaining double unknown kth column pair as a special case after everything is done. Now this, if we take it together, and we have the full algorithm in the paper, gives us a best abstract transformer with worst times time complexity that's quadratic to the number of input bits. Now the main problem here, why is it quadratic, is that basically we cannot compute the hk function with standard multiplication, because we need to do some bit masking and addition instead. And such an instruction just isn't available to us in normal processors. So we have experimentally evaluated the implemented algorithm, and it is available on Figshare under the CC0 license. The link is available from the paper references. And we have computationally verified that the naive and fast algorithms are actually completely equivalent, give equivalent results for n at most 9. After then, it's just infeasible to compute every input possibility for the naive algorithms. Now, if you look at the figure 1, we can see that basically, based on the number of input operand bits, the naive algorithms, both the addition and multiplication, just perform completely exponentially. And these are completely naive algorithms without the wiggling with basically just treating the x as a possibility, but treating every possible possibility and then filtering them. But that would give similar result. It would be exponential in either way. So if we look at the fast algorithms instead, we can see that fast addition is extremely fast. And fast multiplication gets faster than the naive one for about 6 operand bits. At 8 input operand bits, it's really already much faster. Now, if we just look at the fast algorithms with more input operand bits, and this is all for random input combinations, we can see that actually for the random inputs, fast multiplication doesn't exhibit very noticeable quadratic behavior for random inputs. So that is quite nice. And fast algorithm addition is computable almost in no time. And fast multiplication is still on a normal desktop computer, computable above 100,000 operations per second, even for 32 input bits. Now, if we can also look at the dependence on the number of unknown bits. And we can see that basically if we fix the number of input bits at 32, and just vary the number of unknown bits in each input, we get something like this, where the fast multiplication is at its fastest when all of the bits are unknown, because this means that immediately there are double unknown kth column pairs for almost every k, and immediately this implies that Rk is x. And on the other hand, we can see a peak at about 6 unknown bits in each input, but it is not very prominent. It is still very fast. So, in conclusion, we have generalized the resolution of bitwise operations with 3-valued logic, which was done previously, without considering the operations as basically their own thing to a forward operation problem. And we have devised a novel modular extreme finding technique with which we can construct the best abstract transformers. We have proven its correctness in the paper. And we have found the best abstract transformers for addition in linear time and in multiplication in quadratic time based on the number of input bits. And we have implemented them, and they are working quite well. And this is easily generalized to subtraction and general summation. So what we could do in the future? Well, we want to use it in our actual model checker. We didn't have time and space to write it down in this paper. We could try to resolve some other operations, such as division and remainder. The problem is that such operations do not have the pseudo-Boolean operation function that yields itself to basically doing this kind of trick with congruencies and getting the 2 to the power of k step. So this basically gives us abstract transformers, but not the best ones. Operation fusing could be quite interesting. For example, basically, if we have multiply and accumulate instructions, we could try to resolve the multiplication and addition as one single operation without basically doing them sequentially, which could introduce more over approximation. But the last but not least, in fact, probably the most important, is generalizing this to a general operation problem where the outputs can be pre-restricted as well. So what this means is basically that backtracking would be possible And it would be possible to use this with like, well, constraint satisfaction problem solvers and so on. But the problem here is that where we could treat every bit independently of each other with the forward operation problem, here the bits that are pre-restricted play a role in the output of each bit. So this is a much harder problem, but one that we are trying to tackle right now, and hopefully we will have some good results in a few years. So thank you very much for your attention, and if you have any questions, I would be happy to answer them.
Yoni, are you still there? Perhaps you can ask, start with the questions in the room.
Yes, it just took a few seconds for my camera to work. So we have a question in the Q&A tab. I don't see how to present it, but if you can present it, it would be great. Meanwhile, I will read it. Yeah. Any chance of a subquadratic abstract multiplication operation via Suba like divide and conquer combine approach?
I'm not sure if I understood the second part of the question, but basically the multiplication is just limited by the fact that we cannot compute the HK operation. There are some other problems that we outline in the paper, but technically this could be possible if we had a special instruction for computing an operation like this. We cannot rule out that it is possible to do this in a subquadratic worst case scenario, but we have tried it from many angles and we did not succeed. So we cannot rule it out nor say that we have found anything better. So if that answers your question.
Yeah, looks like yes. I don't see more questions here. Are there any questions in the in-person session?
Yeah, I have one question. So you explain how you compute best abstract transformers for addition and multiplication, and for many bitwise operations it's rather easy. But there is one bitwise operation where it's maybe not that easy. Is when you have a logical shift with a variable length. So have you tried to study this particular problem?
Yes, because basically, the forward operation problem is basically well, we can compute it like this. Obviously, we can compute it easily by transforming into the bit shift. With the general operation problem, where we have restricted outputs, then it basically seems to look like it that it is easy to do multiplication for the powers of 2, but not any other basically not for multiplications by numbers that are not powers of 2. It seems that basically this is kind of a special case that is easy because we are working in a binary system where basically multiplying by a power of 2 is equivalent to a left shift, if that answers your question.
Yes, thanks.
More questions in person?
I don't see any other questions right now.
Okay, great. So it's